Um, Guys, I'm Dr. Annan. I know some of you know me. Some of you maybe never had me for a class before. It's great either way. I've been here quite a while as a professor. And I do apologize for last week. I want to I checked all the notes and the videos you guys watched, and I really appreciate you helping me with that because I was still on the road. I actually drove into town like 2 days ago. I'm still kind of hungover from that. And I do appreciate your flexibility as I try to start a new semester. I have this motto that I work hard and I play hard. You'll notice I'm around a lot and I work really hard when I am here, but then when I'm not here, I'm like usually playing hard, which means I'm like on top of some mountain somewhere around the world. And I was literally just coming down from there like last week. I was a little late getting back. And so I do appreciate your flexibility with kind of this weird start to the semester with the videos and stuff. But it seems like at least from the notes, it looks like everybody was kind of picking up on that and it was making good sense. I hope that's the case. If there were some things last week in the notes or in the videos where you had some issues or questions, concerns, anything like that, I hope that you will feel free to, of course, bring them up to me. I am now fully back. I have office hours. Tuesdays and Thursdays are the days I have my classes, so I will be on campus pretty much morning, noon, and night, which means you can come to my office hours in between my classes on Tuesdays and Thursdays. I also will normally have hours on Sundays and Mondays. I know right at the beginning I was still kind of in limbo, but I should most of the time be able to do that. If you're trying to catch me in a little bit of a quieter time, where it's not sort of a frenzy, because remember, I do have 3 classes and almost 100 students. I generally do find those evening hours, they're kind of at off times. One of the reasons I like to do those hours is for those students who are just really frustrated with trying to catch me on Tuesdays and Thursdays. It's usually a little quieter and calmer, and I have more time. You can also drive right up and park in spot number 1 right outside of the building. What a concept, right? This never happens during the middle of a crazy week. So yeah, I just want to really encourage you to stop by, especially if you haven't had a chance to introduce yourself yet. Feel free to stop by and say hello to me. I'm down in the basement of the building. I like to tell the story, which is a true story. When I first came to Cal State Fullerton, they put me in this nice office right with the hallway with all these other professors up on the 3rd floor. And I met all these great people that were here, and it was a wonderful deal. And then after about 2 years of that, the department chair came to me and said, oh, we need you to move. And so they moved me down to the 1st floor. But they sold that to me by saying, okay, you won't be next to all these great colleagues anymore, but you'll be right across from the math office. I was like, perfect. I don't have to walk more than 10 feet to get anything. So I was there and it was great. I really enjoyed being there for a while. 2 years after that, this time the dean comes to me. I'm starting to get worried. The dean comes to me and says, oh, we need you to move again. And I'm like, oh, where am I going this time? And she says, down to the basement. And I'm like, okay, so I've been here 4 years. I started on the 3rd floor. Then I got moved to the 1st floor. Now I'm down to the basement. Is there some kind of a hint that I should be getting? It's like they're trying to keep me like out of sight, out of mind. I'm like, oh boy, I guess I'm not doing too well here so far. But actually, once they took me down there, I realized, oh, I get to hang out with the students now, right? It's like the best scenario instead of all these administrators and so on. And so, we can like throw parties down there and nobody's gonna. That room outside my office is always open. Even after the library gets shut down, you can still be hanging out down there. Nobody's gonna bother you. So actually, I've been pretty happy down there. Yeah, so we'll see if they ever ask me to move again, but I've been down there for quite a while now. I'm pretty sure it's going to stay that way. Yeah, so I encourage you to come to office hours. Also, if you do want to go home, you're like, I don't want to, Dr. Ann has all these late hours because I'm a night owl, by the way. All right, you'll catch me in the evenings a lot because I just stay up late. But if you want to go home and you don't want to like have to just kind of hang out there for all those hours, I will always have my office hours in Zoom as well. And a couple people have already come into Zoom to talk to me. So I'll always be doing kind of dual modality. So feel free to just head home and then log on to Zoom. I'll be available that way as well. So I try my best to be, as available as possible. If my hours don't work for you all the time, you can also shoot me emails to ask questions, or you can just set up an appointment to meet with me at some other time and we'll work it out. Like we'll figure out what works best for everybody. But I am really excited about combinatorics. I have taught the class for quite a few semesters. I mean, I've probably taught it 6 or 7 times, but there was a hiatus that I had after about 2014, because there were suddenly these other professors that wanted to teach it. It's always so inconvenient when they want to teach the same thing you do. So I sort of had to step back and get under this rotation system with these guys. And it was just about going to be my turn again. And then this other professor decided he was about ready to retire in a couple of years, and this was his favorite class to teach. So of course I had to step aside for that. So I spent 2 more years teaching something else. I finally got back into combinatorics here these last couple of years. So I'm really stoked about the topic. I will tell you with combinatorics, it's quite different because I've taught all the classes in the department almost. I really have. Maybe a couple of geometry classes that I've managed to slither away from. But for the most part, I've taught almost every class. And this one feels different somehow. And I think I know what it is. And it's something that you guys will probably also recognize, which is that this class and this topic does not have heavy prerequisites. Like you don't have to come in here having taken 5 calculus classes before you can understand combinatorics, or just have this huge broad background. I know officially on the books, I think there's 302 and 307 are mentioned as prerequisites. That's mostly just for a maturity reason. It's not like you really are going to see a lot of linear algebra here. So in a way, that's kind of nice. You can just kind of jump in headlong into this topic without having to worry about how many things you're going to remember from your other classes. But what is perhaps the challenge with this subject is that it often requires sort of subtle and clever thinking about the problems that is somehow it's not rooted in like how many formulas you've memorized, or how well you paid attention in your other math classes, right? It's really sort of question by question, problem by problem, topic by topic, that you really start to sense that, okay, although I don't need a lot of background for this, I can't really just walk and chew gum at the same time while I'm doing combinatorics. I have to actually really be focused into my thought process about the topic, because one little subtle thing, like the way I phrase a question or the wording of something, can make a massive difference in sort of how you have to approach it. And sometimes I actually find that the biggest problem is just the communication part, like the English, what's the question actually asking, right? How many necklaces can you make that have 5 red beads, 3 green beads, and 2 blue beads? Do we understand that question? Do you mean necklaces that are allowed to rotate and flip over, or do they have to be static in a particular position? These little subtle things actually completely change what the answers are going to be. So I want to encourage you, if you run into questions in the homework where you don't quite know what's being asked or whatever, heck, that's a good time to come talk to me or your classmates and just hash it out. What is this question really saying? Because it can be kind of frustrating if you're interpreting the question one way, but then because of one subtle word, it's interpreted or supposed to be interpreted in a completely different way. So I'm not trying to scare anybody about it. I'm just trying to give you a heads up that this does come up in this class a little bit. So just kind of be ready for it. You're going to see it from time to time. Okay. Couple other things. I've got my laptop up here. It barely works. I'm going to get a new one tomorrow. But I will be recording these lectures and posting them in Canvas. This is not so that you can all decide to stay home on Tuesdays and Thursdays and just watch the videos later. No, this is more, let's say you have an emergency that you can't come to class maybe once or twice for some reason beyond your control. Then you could still watch the video for the class. Or maybe 3 weeks from now, you would like to review something that you saw. You remember seeing it in class, but you want to just hear the discussion again. because I'll have those videos up, you'll be able to do that. So that will be in Canvas for you as well. And I encourage you to take advantage of that. Finally, homework. There's plenty of it. There will be plenty of it. I'm warning everybody now, heads up ahead of time. You signed up for a class that has a lot of practice associated with it. And again, it does go back to what I was just talking about, that you really have to get used to these subtle nuances of the subject. So do be prepared to put a good bit of time into this. The good news about it, though, is, of course, I'm also going to be working very hard because I want you to learn it well. I want you to understand it and appreciate it and enjoy it as much as I do. So take advantage of one another, of my office hours, and the chances to sort of interact whenever you can to learn about the material. I'm also going to do review sessions before we have exams and stuff like that, try to give you lots of practice. So you're going to want to try to dial in as much as possible. This is not a class that you can kind of just be a spectator. I'm just going to sit back and just kind of do the bare minimum to kind of get through it, right? You need to have the attitude, okay, I need to go full blast on this one. And I think if you do that, you'll enjoy it more, you'll learn more, and you're certainly going to do better as well. So I know we're all busy. You have other classes, you got other obligations and things to do. I totally get that. So let me know if, there's occasionally something comes up, like you need a little extra time here or there. I'm totally good with that. Just keep me posted with how you're doing. Speaking of the homework, there is an assignment due this Thursday. I am going to have office hours today as well as Thursday. So if you have questions, want to talk about any of the problems as you've been working on them, by all means, feel free to reach out to me. Try to get it into Canvas by 11:59. I'm not necessarily going to grade it right that second, but I'd like to just get them all collected. I will be posting solutions to the homeworks so that you can review them later after the fact. And I will be grading some of the problems. Basically, it's a pretty big class. I'll be honest, I think this is maybe the largest combinatorics class I've ever had, and that will affect my ability to grade everything. So since I won't be able to do that, I will probably pick and choose some things to grade and then ask you to just read the solutions that I'm posting on the Canvas site and just kind of cross-check your answers with those solutions, then follow up, of course, if there's questions from there. So that's the first assignment. The first assignment is basically about the videos that you guys watched last week. I think all of that content was in there. The second assignment, which will be due a week from today, is based on, starting some of the chapter 2 material on permutations of sets and combinations of sets. So you can get started on that, of course, and ask me questions about that as well. So I know you've all watched the syllabus video. I'm not going to go through all those details again. Does anybody have any questions though before we get started? Yes, Nikolai.
What is the Lagrange theorem of this class?
Oh, that is a tough. Okay, I'm glad you brought that up. So what Nikolai is referring to is that a lot of classes that you take, there is sort of one crux result that is sort of the foundation of it that's being built. Like, for example, when you take Math 350, which is the real analysis class, of course, the fundamental theorem of calculus comes to mind, right? This is like the big enchilada. At the end of the semester, you get to that. It's sort of a natural question is, well, what is that analogous thing in combinatorics? And so this again feeds back to what I was talking about a few minutes ago, that this class feels different than some of those other courses in the curriculum, in the sense that it is more of a, what I will call, hodgepodge of different topics, right? We're going to do some graph theory, which has nothing to do so much with some of the counting strategies that we have, which in turn doesn't have so much to do with sort of analyzing combinatorial objects for their own intrinsic values. So we're going to be doing a little bit of all of these things. And so it's kind of hard to give you, I could give you a short list, but I think I will maybe do that later. Okay, but that is a very good question. Does anybody else have any questions before we kind of jump in today? Anything? I know you've watched the syllabus video, kind of watched some of the stuff about the pigeonhole principle and some of the applications of it. So many of the problems in combinatorics are actually easy enough that like a 10-year-old can understand the question, right? Of course, answering the question is a different thing, but they can understand what the question is asking, and they can be framed in a very simple way. So that's kind of appealing as well, especially for those of you who are thinking about going into teaching, because you might have kids that are curious, right? And can think about these real world questions. I encourage you, as a way of kind of enhancing your own understanding of the material, to try to actually write questions yourself. That you could maybe share with somebody, share it with me, see if I can answer it, see if your classmate can answer it, see if it makes sense to you, see if it makes sense to other people. It's actually not a bad exercise to do, because it is easy to sort of think of these questions. And so you can write them down, and you'll start to appreciate that sometimes the questions that you come across are actually very hard to answer in the combinatorial sense. Whereas other questions might be somehow like trivial to answer. And it can take the whole spectrum between there. So yeah, I encourage you to kind of get creative for yourself as well. But before you take a quiz or an exam in this class, try writing a few questions, try to write your own exam, right? Put yourself in my shoes and think, well, what kind of question would he maybe ask? And see if you can like tinker around with it and come up with something. It's actually a masterful way to learn a subject, is actually by thinking about questions and actually almost like putting yourself in the role of the teacher. I used to do that, by the way. I didn't have a life when I was growing up. So I would go down to the university. I would like go into a classroom. I'd lock myself in the room and I'd just start lecturing to myself the material. I'm not suggesting everybody has to do that, but it worked for me, right? And so think about what works for you in terms of trying to kind of get a handle on this material. I hope it'll be a fruitful exercise. Okay, I think that's all I need as far as preliminaries go. So what I'm going to do, we're going to do a little group work today. Before I get to that, however, I will usually start class with a quick summary of at least some of what was going on before we had this class. So I know last week there was a whole bunch of videos, so I didn't want to put the whole video stuff up there. I just kind of put a quick little reminder here about permutations of sets. I especially encourage you to be reviewing your notes, especially on Monday nights and Tuesday mornings when it's been a long 4-day weekend and you're trying to get back into the flow of it again. So sometimes I'll put these up here to just kind of get the wheels turning again from where we left off. The last video that you hopefully have watched already last week was about permutations of sets. So of course, a set is a collection of objects. And so these objects could be put into some kind of an ordering, right? We can like lay them down, first object, second object, third object. And when you're talking about permutations, you're actually keeping track of that ordering, right? So if these two people are sitting like this, but then they switch chairs, that's a different permutation as opposed to what I'll talk about shortly, which is combinations where you don't care about the order. But permutations do keep track of ordering. And if I have an n element set and I want to take R of those elements, so that might not be all of them, I'm going to take some of those elements and I want to not only take them, but I want to put them in order and keep track of the order. There's a notation for how many ways there are to do that. This is P of NR. You'll actually sometimes see this on one of those old-fashioned calculators for the button that has a P with an N and an R underneath of it. And that's just referring to R permutations of an N element set. And so this is the formula, this is the notation for it. The formula for it is, so you start off, the first object could be any one of the N objects in the set. After that, the second object that you pick would be one of the remaining ones. The third object would be one of the remaining ones after that. And so this is like this falling factorial type of product that you see. But of course, it doesn't have to go forever. If I'm only picking R objects to put into this permutation, then you'll notice that there would only be R factors here. And so that's actually why we're stopping right here with N minus R plus 1. So I kind of talked about this in the video, right? This falling factorial that stopped can be written, of course, as a quotient here of two full factorials, right? So you take n factorial, which goes all the way from n down to 1. And then on the bottom, you take n minus r factorial, which starts at n minus r and goes all the way down to 1. Most of those, well, all of those terms in the denominator will cancel with something from the numerator, leaving just these factors left over, right? So this is permutations, putting these objects in order. So that's always a question to ask yourself in combinatorics when you're counting arrangements of objects, which is a lot of what this subject is. Does the order of the objects matter? I wish I could tell you that it was always a simple yes or a simple no. But of course, we know that's not true, right? Like, even if I ask you, well, how many ways we're going to do this one soon. How many ways are there to lay out the letters of Mississippi? You would say things like, you would probably tell me that if I switch this M and this I, that would give you a different permutation of those letters. But obviously, if I switch these two S's, it doesn't change what I'm looking at in any way whatsoever. So does the order matter? Well, now it's like sort of yes and sort of no. So it's not quite as clean cut as you might think, but it is still a good exercise to ask yourself. Does the order of the objects matter? Yeah.
On a note of word like Mississippi.
Yeah.
How would the question be phrased if like the S's were distinct? Like S1, S2.
I would, well, if I wanted to make them distinct, I would just come up with an 11-letter word that had no repeated letters.
Yeah.
That would be easier for me to do that. If I just wanted to ask you how many ways are there to arrange the letters of Mississippi, I would just ask the question like that, and I would expect you to know that two S's look the same, but an S and an I and an M, they all look different from each other. Yeah, so that's the kind of subtleties that we have to kind of keep track of. Okay, well, what I didn't have you watch any videos. Are there any other questions, sir? Sorry. Sure. Oh, I'm so excited to be doing this. It's you know, I sort of have two lives. I live by the motto of work hard, play hard. So I work really hard most of the year when I'm here, and I love doing it. And then I also play hard in the summer. I go climb mountains and travel the world and stuff. And I love both parts of my life. And I always kind of like coming back. Like, you know, I was kind of tired of climbing mountains by the end of the summer, and I'm ready to go back to math again. But then by the end of the year, it's like, okay, I'm ready to take a break from math for a while. But I always start the new year kind of, which is where we're at right now, kind of reinvigorated again, which is really a really great feeling. So what I would like to talk about next is kind of the companion topic to permutations of sets, which is this idea of combinations of sets. It's actually a very different thing. So this is actually the thing I'm going to discuss right here. Combinations of sets. And as you've already noticed, I kind of started out of order. We did the pigeonhole principle, which is in chapter 3. I'm kind of going backpedaling now into chapter 2. This is actually covered in section 2.3. By the way, if anybody is having any trouble getting the book, I have, well, I think I sent you an electronic link to it. If you're still looking for a copy, I have like 4 of these in my office. You can come by anytime if you need to borrow one. Feel free to do that. But I try to line up the sections from the book with my headers here. And in this case, when you're talking about combinations of sets, here repetition is not allowed, and order doesn't matter. Repetition not allowed, order doesn't matter. So that's really the difference, right? Permutations, the order does matter. So over here, we also are saying repetition, I should have put this in my recap as well. Repetition is not allowed, and order does matter. In other words, order matters. So you see the difference? Here it says order matters. Here it says order doesn't matter. You know, we can ask these two questions. Is repetition allowed and does order matter? And of course you have what, 4 combinations of answers? Yes and yes, no and no. yes and no and yes. And we talk about all four of those categories. And then I throw the Mississippi problem at you where it doesn't really fit into any of those four categories. But at least this is a good place to start with trying to kind of understand this topic. So let me give you like a typical example here. And guys, I have no like agenda for this. If you have questions, if we need to go off on a sidetrack or talk about something else, just let me know, because that's the fun thing about these upper division classes. Nobody's like looking over my shoulder. Did he cover the syllabus or like what exactly? Because this is not like a prerequisite for something else. So I don't want to go too fast. That's all I'm trying to say. If you've got some questions, let me know. So a typical example here would be poker hands from a single deck of cards. Is everybody here familiar with the standard 52 cards, you know, where you have, what is it, 4 suits, hearts, spades, clubs, and diamonds. And then in each of those, there's 13 different kinds. You go from the ace all the way to ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king. And so together that's 52 cards. That's what we're talking about here. I'm going to make it a single deck of cards so that repetition is not allowed. I don't want to get the ace of hearts twice. But usually when you're playing cards, of course, it doesn't matter what order they're in, right? You can shuffle them around in your hands. And it doesn't make any difference in terms of playing the game, whatever it is you're doing with the cards. So that's a good example to be thinking about. Let me give you a quick definition then of what an R combination is. I've got the R permutation definition over there. But let's do this. Let's make a definition. Let S be a set with N objects. And then here we'll define an R combination. An R combination of S. This is what is called an unordered, right? Order doesn't matter. It is an unordered selection of R objects from S. It's an unordered selection. Maybe I should emphasize that word. We're not putting them in order at all. We're just choosing the objects. So, you know, it's, again, we can ask very similar questions that are quite different in how they would be answered. If I'm trying to choose 5 players for a basketball team, I'm not necessarily putting them in order. I might take everybody in this room and however many that is and choose 5 of you. But I don't really care about what order I pick you in. There's a different number of ways to do that than if I say I want to pick a, I don't know, a captain and a center and a guard and all that, right? Then putting certain people in certain positions and then swapping them would make a difference. So this is kind of what we're talking about. But here, we're just keeping everything totally unordered. Let me write down an example of this. Maybe I'll do it here. This example is going to be kind of parallel to one that was in the videos that you watched last week. So it kind of makes sense that I put this one here. Let's write down the 2 combinations. So in this case, R is equal to 2. The 2 combinations of the set A, B, C, D, and E. And let's write down what they are. And so you might remember in the videos last week, I asked you to write down in the video, I said, let's write down the 2 permutations of these 5 objects in this set. But now here, I don't care about the order. So AB is the same as BA. If I was trying to write down the 2 permutations, I would list those as 2 separate arrangements. But if I'm just writing down the 2 combinations, I would write down AB, but I would not write down BA because BA is the same as AB. And because I don't care about the order, what actually kind of makes sense to do here is to just always put the earlier letter first. Just make that as a convention. You don't have to do that, but it just makes life easy. So I'm gonna write AB, but I'm not gonna write BA. I'll write AC, but I won't write CA. I'll write AD, and then I'll write AE. And then that's all the ways to include the A in the combination. Then I can start with B, and I can go BC, BD, BE. And then we start with C, we have CD, CE, and then finally D, right? So we're just writing them in that order. Of course, if I was doing the two permutations, which should be in your notes already, you would have every one of these written down again with the two letters in the opposite order, and you'd be counting them as different from the 10 objects that are already up there. So there's 10 of these here, right? There would have been 20 of the two permutations of that set. Right, okay, so does this make sense? By the way, let me know, are there any questions so far? Pretty clear? I'm trying not to get too crazy here with this. So of course, we want to talk about how many of these combinations there are. And of course, we're going to have a notation for this as well, which is going to go along with the notation that is in the recap over there on the left. So the number of our combinations of an n element set is, so on your calculator, that button might be NCR. Okay. Or we could write it as C of NR. Okay, so this is totally compatible with the permutation notation we have over there on the left. But it turns out there is one other notation that gets used and is actually somehow it's caught fire. It's a more common way to write this notation, which is you just put the N on top of the R and put some parentheses around it. This is another notation that is very common. The way we read this is N choose R. So that word choose is there to really focus our mind that, okay, we're choosing a combination. We're not putting them in order, we're just choosing them. Yeah, that's the idea. Okay, so just as a quick example here, if I wanted to know what is 5 choose 2, right? If I have a 5 element set and I want to count how many 2 combinations I have, well, I can just do that here. There's 10 of them, right? So that is equal to 10. It's a very simple number to work out. Okay, everybody with me? Now, there's some special cases. I guess I'll write these here. I like to get kind of the boring technicalities over with first. So if I wanted to know like what N choose N is, like this would be, I have 30 people in this room and I want to choose 30 of them. You could say I have no way of doing it because I guess I would think you have one way of doing it, which is you just have to take everybody. That is kind of the convention. It's just equal to 1. And it's actually the same as, if you said how many ways are there to choose 0 people from the room. And I would say there's one way to do it, which is you just declare that you're not taking anybody. It's kind of the way to think about it. We can also do, another very easy one is just N choose 1. If I have N objects and I want to choose one of them, how many ways are there to do that? N, right? Okay, exactly. So there's N ways to do that. And that's also the same, just out of curiosity, that is the same as N choose N minus 1. Because you can imagine, this is going to be useful for something I'm going to show you in a second. You can imagine that if I wanted to choose all but one object from the set, what I could do is I could instead choose one object that I won't take. And then by default, everything else gets chosen. So it's almost got to be the same amount. There's some kind of a symmetry to it, right? So these numbers should be the same. And in fact, you will also not be surprised that in general, I'll put dot, dot, dot here because we can keep going. It turns out that n choose k, if I want to choose k objects from a collection, a set of size n, it's the same as not choosing the n minus k other objects. So this is actually always true. This is for all k ranging from 0 all the way to n. So there's really no other values of k to think about than those. Obviously, you know, if it doesn't make sense to have k be a negative number, you can't choose a negative number of things, and it also doesn't make sense. Well, it doesn't really make sense for k to be bigger than n, unless you want to just say that there would be 0 ways of doing that. So that's just some technicalities. But what's maybe a little bit more interesting question that I'm sure that this is going to come up, so I might as well nip it in the bud here a little bit. The question that would be more maybe natural to ask is, how are P of NR and C of NR related? Okay, and I just erased the P of NR formula, so let me put it back up here again, just so we can kind of have it in front of us. So that's P of NR, the R permutations of an n element set. I just want to kind of talk about how these numbers are related. Anybody have an idea what the, at least with respect to like the formula, how these would be related? Go ahead.
The combination is permutations divided by R, or divided by, yeah. Divided by R.
Say it again. Ah, there's an R factorial in this. That's absolutely right. So yeah, the idea here, guys, one way to think about it is you could first choose the objects, just choose them. I choose who's going to be on my basketball team, right? And then one more additional task is to then assign positions to them, right? So what you could say is that P of NR, if I want to put them in order, if I want to put R objects in order, what I first do is choose the objects. There's this many ways to do that, and choose R. And then once the R objects have been chosen, I then put them in an ordering, right? And that would just be R factorial from there. So this would be the formula. So this is, by the way, when I write something like this down, I always like to kind of put a little justification here. So this is choose R objects. And then this little R factorial is arrange them in order. Okay, so that's exactly what it would be. And so actually, if we want, we could then solve for C of NR, which would just be P of N comma R divided by R factorial. Just solve it the other way around. And I can now take the formula for the permutations of the R permutations of an n element set and feed that into here. And what you'll get then is n factorial on top. And then on the bottom, you have n minus R factorial times R factorial. Okay, so that is the expression. And you see here, you'll notice that if I replace the R with n minus R, so everywhere you see an R, change it to n minus R. You see that the denominator is really the same. The two factors are just in the opposite order. Does everybody see that? If I take this formula here and everywhere I see R, I change it to n minus R. Then this factor moves here and this factor moves here. That's consistent with what I'm saying right here, right? So that's kind of almost like a proof using the formula that is true. So I could add that here too, right? C of n, choose n minus R. It's all coming down to the same value. This is actually stated in the book as a theorem. So I believe this is theorem 2.3.1 in the book, and it's kind of just a common sense thing. If you just think about it for a second, it kind of makes sense. Okay. Let me do a couple, how's my time coming here? Okay, let me do a couple, I said we're gonna do a little group work. Before we do that, I want to do a couple of examples with the combinations as well. And then we'll take a little break from this and let you guys try some things out. Yeah, so let's just do some examples involving combinations. Again, there's no prerequisites for this. It's sort of more like we just have to kind of be focused and think carefully about kind of what the question is actually asking. So here's the first example I want to do. This one should be pretty fast. So let's let S be a set of size n. Okay, so I have a 5-element set here. The number of subsets of size k is, and now it's open for you guys to answer. So how many subsets of size k would you have? Remember that in a set, the order doesn't matter, right? So that's why we're talking about this right now. It's combinations that we're looking at where order does not matter. What does anybody think the answer is going to be here? And don't be afraid to try something, because again, sometimes the answer is like really way more complicated than we think, but then other times it's like sort of just right in front of us. You have an idea? It's just n choose k. Yeah, it's like a trick question, guys. It's just take the n objects in the set and choose k of them. Like it literally is the mechanism for making a subset of size k. You just choose the elements and throw them into the set. It's just that easy. Okay, great. What I wanted to, so I had a reason for putting this as the first example, which is I have a more interesting example now to build off of that, which is that is the question of how many total subsets does S have? So this is a follow-up to the first example. So I have a set of size n, and I would like to know, like, what's the total number of subsets that we could have? Now, keep in mind, your subset could have size 0, it could have size 1, it could have size 2, and so on. Would there be a way of kind of, using the first observation in the first item to help us answer this question? Luke.
You will sum from k equals 0 to up to n of the n choose k.
Exactly. You can just add them up. You can say subsets of size 0, there's this many, right? Subsets of size 1, there's this many, right? Subsets of size 2, there's this many, and so on. And we could just go dot, dot, dot all the way up to n choose n. This would be the answer. Okay, and so Luke gave it to me in summation notation, so I could write this if I wanted as a summation where k goes from 0 to n of n choose k. That's exactly what it is. And that's fine and dandy. Notice, by the way, we don't have to subtract anything. You remember the problem in the video with the cats and dogs and birds, or whatever it was, cats, birds, and something. And I said, how many strings have cat in them or bird in them? And then we had to subtract this overlap of like some strings have both in them. Well, here there's nothing to subtract because no sets of size 0 are going to be counted with sets of size 1 or with sets of size 2, or like they're all disjoints categories, right? That don't have any overlapping. And so for that reason, You just add these terms all together. But here's the interesting thing. Does anybody know another answer to the question besides Luke? So let's get away from thinking about the n choose k for a second. Can anybody give me another formula for the number of subsets of an n element set S?
Is that to the end?
2 to the n, that is exactly right. This is also equal to 2 to the n. You know how to explain that one? Or you just had that memorized because it's kind of a cool formula?
I remember that they showed it to us in 280.
Okay.
That's how you like count pretty much like the sets that you can.
See, combinatorics is like in every class. It's all over the place. It's just around us everywhere. Yeah, guys, I can either be in or out of the subset, right? Chris, right?
Yes.
Can be in or out of the subset. What's her name?
Teresa.
Teresa could be in or out of the subset. We each have two choices, right? Everybody in this room, if there's n of us in this room, we're either in or out. And it's an independent choice. Whether I'm in or out doesn't affect whether Kevin is in or out, right? Everybody is independently either in or out. And so we take two choices times two choices. This is the multiplication principle, classic example of it. And so guys, this is actually a fairly well-known combinatorial formula. And later in the semester, we're going to talk about what's called combinatorial proofs. We're going to prove that two expressions are equal to each other by setting up some scenario which we can count from one perspective and get one answer, and then think about it from a different angle and get a different answer. But of course, since we were counting the same thing, either way, it has to have the same answer. So they must be, see, it's a neat way to prove things in combinatorics. So yeah, so that is a very famous formula. It can also be proven as a special case of the binomial theorem, which is another thing we're going to talk about. So there's a lot of perspectives on this result that we can have. Okay. Yeah, this is also in the book. This is theorem 2.3.4. So, by the way, the book, generally I like this book. I think it is very comprehensive. I think it is written in a conversational tone that is appropriate for this level of a class. It is a little bit reaching. It likes to go off on lots of things that I'm not going to talk about here. So if you're trying to read every word of every page of the book, you might get a little frustrated and feel like, well, he didn't talk about that. And oh, this isn't looking familiar to me. You can kind of gloss over in terms of what I'm going to hold you responsible for. You can gloss over stuff that's in the book that I never mentioned. I probably won't be asking you about it, right? It's much more important to focus on like what we're actually doing here, because that's already 15 weeks worth of material, which is plenty, I think. Okay, let's do an actual like more physical application problem. This was kind of just to show you how you can use these combination expressions to count subsets. But there's some other problems here. I talked about poker cards. Let's do a poker problem here. How many 5-card poker hands contain, and now I'm going to give you we're going to do several parts here. So I just want to kind of do part A first, which is first of all going to be no restrictions. So if I ask you that, keeping in mind that order does not matter when you have a hand of cards, can somebody tell me how many 5-card poker hands would be possible using a standard deck of 52 cards? Fernando? It's just 52, choose 5. Exactly. 52, choose 5. That's all there is to it. Of course, we could get a numerical value for this, but I actually don't care about that so much here. You know, you don't have to like work it out with a calculator. You can just like leave your answer like this. I should point out, however, that, you know, this would be 52 factorial divided by 5 factorial and 47 factorial, right? And just so you can kind of see, I want to imagine that I cancel the 47 factorial into the 52 factorial. What you'll get on top, what will survive that canceling would be just the just the factorials from 52 down to 48. And then on the bottom, we would keep the 5 factorial. This is just a kind of a neat little trick. What you're doing here is you're factorialing your way down from the top, the same amount that you factorial up from the bottom. So you start with 1 and you go up to, well, the smaller number here is 5, and then you do 5 steps down from the top. Of course, this could be simplified further. I'm not going to bother with that, but I just wanted you to sort of see that that's one way to kind of clean it up a little bit if you wanted to. Okay, so there's not a whole lot there. Let's take something a little more interesting here. What if I said, how many 5-card poker hands contain 4 of a kind? We need to, first of all, make sure everybody understands. If by the way, if you don't know how cards work, you might want to go buy yourself a deck of cards for this class. Might be helpful. Or we'll keep some in my office. I'm pretty sure I have a deck of cards there to play around with that. 4 of a kind just means you actually have all 4 suits of one of the kinds. So it could be 4 aces, it could be 4 sixes, it could be 4 jacks, whatever, right? So that would be the question. Is how many poker cards contain 4 of a kind. So let's think about the solution. This time we might have to write a little bit more down. What are, if you were in charge of constructing a 5-card hand that had 4 of a kind, where would you be making some choices? Yes.
13 cards from each suit, right?
One more time.
13 cards from each suit, right?
There's 13 cards from each suit. So that 13 is going to come into it, isn't it? Right? Because I have to choose, is it going to be 4 aces, or is it going to be 4 threes, or is it going to be 4 queens, or what is it, right? So 13, I like the 13. Let's say I've decided it's going to be, so just in your mind, or in my mind, what I like to do is just imagine I've made that choice. I have decided it's going to be 4 aces. There were 13 choices, and that's the one I've made. So I've got 4 aces and
12 choose 1 for the other card.
okay, I have to choose one other card, and I could think of that as it has to be one of the other kinds. So if I'm going to have 4 aces, that was my first choice. Then Amber is saying, well, okay, now I have to choose what the other card would be. Maybe it's a queen. So there'd be like 12 choices to choose that. So let's write down some reasons here. So this is going to be to choose the kind to have 4 of. This is actually the way I want you to kind of do this when you're turning. Guys, when you're doing problems like this in the homework, make sure you have these little justifications down. I don't just want to see a number at the end. I want to understand where the number comes from. Okay, and so then what Amber is saying here is choose another kind other than the one that you have all 4 of. Okay, so let's say we've decided that it's going to be a queen. What else do we have to choose? Which suit it is within that kind. So that would be 4 choices, right? Hearts, clubs, diamonds, or spades. So this would be choose the suit. Like I see here, I don't have to choose the suit because I'm taking all 4, right? The 4 of a kind, that's 4 aces, right? I don't have to decide, well, is it diamonds, hearts, clubs, or spades? Because I'm actually by default grabbing all of those. There's no flexibility with that. Now, some of you might have actually thought that the answer here would just be 13 times 48. And you would have just said, I'm going to choose which kind to have 4 of, and then I'm just going to grab one of the other 48 cards from the deck. And if you wrote that down, if you wrote down 13 times 48 and you wrote that explanation, totally good with that, right? It's a slightly different way of kind of organizing your thinking, but it's also totally legitimate. I actually don't care if you multiply this out or not. Okay, the actual numerical value doesn't really matter to me. Okay, let's do another one. We'll do a couple more of these and then we'll switch to some group work mode that I don't know. I kind of feel like playing cards now. It's been a long time since I've done it. I go through Vegas all the time, but I never stop in there. I have a feeling I could do pretty good. But I've never actually tried it. Hmm?
Don't let them catch you.
I know. I don't wanna get myself in trouble. Okay, let's try another one. How many 5-card poker hands contain exactly 2 suits? That's it. So you have to have, either hearts and clubs or diamonds and hearts. Spades and clubs, whatever. So this is again, not heavy prerequisite material other than knowing what a deck of cards looks like. It's more about being focused into thinking about like, what choices do we have to make? Can somebody tell me one of the things that we would need to choose if we were constructing a 5-card hand that has exactly 2 suits? Yes.
Have to be like the number that have that suit. So for example, we'd have to choose 3 with the same suit and 2 with the same suit, or 4 of the same suit and 1 of the other suit.
Okay, exactly. We're gonna have to have either 3 cards from one suit and 2 from the other, or we're gonna have 4 cards from one suit and 1 from the other. That's one choice we have to make. What's maybe even a more fundamental choice that we might have to make that at least in my head, would be the first thing to do. Amber?
Which 2 suits?
Which 2 suits? I would probably start by thinking of that. Is it gonna be hearts and clubs? Is it gonna be diamonds and spades? Is it gonna be clubs and spades? What is it, right? So, and how many ways are there to choose the 2 suits? 4 choose 2, because we're not putting them in order, right? So we're just gonna choose the 2 suits. So let's get the solution here. Actually, I take that back. So I'm happy with the 4 choose 2, which is to choose the suits. I do want to point out, we could put them in order. We could say, I'm gonna take the first suit that I decide on, I will take 3 cards from. And the second suit, I will take 2 cards from. Or the first suit I would take 4 cards from, and the second suit I would take 1 card. Like you could say, whichever suit I choose first, I will take more cards from that suit. And then whichever suit I choose second, I would take less cards from that. But I actually, again, that's also okay. I actually would probably do it this way. I would just choose the 2 suits. So in your minds, you can be already deciding, okay, maybe I'm gonna go with hearts and diamonds, whatever it is. So imagine that that's all you've got. So at this point, the clubs and spades have been thrown into the trash, and we're just looking at the hearts and diamonds. Now, from there, we have to make more choices here. Okay, so does somebody want to? So we've got hearts and diamonds. So it could be 4 hearts and 1 diamond. It could be 3 hearts and 2 diamonds. It could be 2 hearts and 3 diamonds, or it could be 1 heart and 4 diamonds, right? It has to be at least one of each, because if you don't choose any hearts, then you haven't used both of the 2 suits that you chose. So how are we going to handle this part? Before you answer, let me just say it one more time. 4 hearts and 1 diamond, or 3 hearts and 2 diamonds, or 2 hearts and 3 diamonds. Notice I'm emphasizing the word or, right? Because there's several methods to doing this one task. What rule am I alluding to here? The addition rule, the sum rule, right? There's cases that are going to be added together, and because I'm doing addition, I better put some brackets here. And now somebody had their hand up and they wanted to try it. Oh, was it?
Oh, yeah.
Yeah, go ahead, give it a shot.
For one of them, it would be 13 choose 3. And then
Okay.
it would be 13 choose 2.
Okay, so this might be, I'm gonna choose 3 hearts and 2 diamonds. Okay, so that would be one case. Okay, beautiful. What would be another one of the cases that we would want to add to that? B?
And the other way around. So 13 choose 2 times 13.
Okay, beautiful. We could do 2 hearts and 3 diamonds. Okay, kind of getting the idea? Or I could do, what else? I could do 4 hearts and 1 diamond. So that would be 13 choose 4 times 13 choose 1. And I'm using combinations because again, the order does not matter. Or I could do 1 heart and 4 diamonds. Just like that. Okay, that's exactly right. That looks really, really good. Let's do another one. Are there any questions on that? Yeah.
Is there like a way to do this with like I guess if a little more from that, it's like, is there like better way of writing them, or is it like, this is it?
This. Are you saying I don't have any finesse?
No.
I get what you're saying. I'm trying to think, I'm not sure how to like make this look more beautiful. It really is a sum. I mean, we probably should say here something like, 3 hearts and 2 diamonds, just to make it clear to explain these terms. But in terms of like writing it out in a fancier single notation, I don't really think there's anything that would be worth the effort for that. This one would be 4 hearts and 1 diamond. This is of course assuming I chose these 2 suits, right? And then this one would be 1 heart and 4 diamonds. Yeah, something like that. That's right. Okay, let me give you another one. I kind of like these. Let's try another one. This next one I have to be a little careful with. Can I just steal this little corner of your table there? Thank you so much. So this next one, part D, is going to be at least 1 club. How many 5-card poker hands contain at least 1 club? So let's give everybody a minute to think about this. Really have to train ourselves combinatorially for these things. I don't care how much calculus you studied or linear algebra or anything like that. This is kind of a different kind of thinking. I hear a few people talking. Why don't you let's take a minute. Take 1 minute. You have a partner. Hopefully you're sitting next to a partner or somebody close by. Chat with them for a second about it.
I was thinking about doing it like 1 minus where you get no clubs. Cause it means you get
Yeah.
at least.
Yeah.
I feel like at least 1 you have from.
I'm gonna work for this first. How are you? Good. Go ahead, Maddie.
I was thinking about doing it with going opposite, so 1 minus where you choose no clubs. Because
Yeah.
at least 1, because then it's at least 1 and you have to calculate getting 1, getting 2, getting all the way up to 13. But we do 1 minus, getting no clubs is the same as.
I was thinking similarly, but I was thinking 52 choose 5 minus the no clubs, like all of the hands of poker minus the hands with no, wait, with no clubs.
But I think.
Yeah, so it's a totally.
I think those are the same.
Okay, that's thinking too, like.
Yeah, because 1 is 50 choose 5.
That's like it's like 100%, right? Like all the, okay, cool.
So if we, so it would be 1 minus choosing no club, wouldn't it just be
52.
Yeah, that's what I would have done originally, but they.
39, 39. Yeah, because that would be if you just subtract the 13 clubs out, right? And then you pick 5 poker hands. So yeah, I like it. 50 choose who's 5 minus.
Guys, let's take a minute. I want to see. I know I hear some good conversations going on. Is there any group that sort of feels like semi-confident that they might have an answer? Do you want to give it a try?
So we did subtracting out all the ones that don't work.
That's a great idea. So in the videos last week, yeah, I hope that one of the things you kind of got a little flavor for was this subtraction trick. The idea of counting what you don't want and subtracting it from the total. So of course we have 52 choose 5 total number of hands. And we could subtract out the violations, as I like to call them. Violations would be any poker hands that have no clubs, right? That's the opposite of what you want. How many poker hands would have no clubs at all? Yeah, if we just throw the clubs away and we say we're not allowed to use those, then I've got 39 other cards, right? I have 13 hearts, 13 diamonds, and 13 spades, and I would choose 5 from there. Does that make sense to everybody? Is that what a lot of the groups came up with? Feel okay about that? This is beautiful. It's totally correct. And you can just say total, and then this is violations. violations meaning no clubs, something like that would be a perfectly good explanation. But I want to throw a little wrench in this though, and ask you about another possible answer, and I want to know if you think that it sounds good to you. I want to make my poker hand have at least one club, so I'm going to choose a club to begin with. And I've got anyone, I could choose anything, an ace, a 2, a 3, a 4, a 5. I choose a club. I just want to get that over with, get my club in my hands. And now I need 4 more cards. So out of the other 51 cards in the deck, after I took that club, I'm just going to choose any 4 of them that I want. Is that going to be correct?
Oh, I thought so.
I tried to make it sound so
That's
convincing.
Exactly.
Just grab my one club. I'm good with having at least one club. And now I'm going to just fill out the hand with any other cards from the deck.
It looks good. to me.
Doesn't it? I thought it looked good too, but you know what? I put this in my calculator and then I put this in my calculator and they're not the same. This is the correct answer. But this is a chance to show you the subtlety that can come up with these kinds of arguments. What is wrong with this? Does anybody think they know what's wrong with this?
Just
Dr. Nava?
Is it exactly one?
Well, no, I choose my one club and then I might get more clubs here. Oh, it could be, additional clubs in the remaining cards. I don't know. Kevin?
You're considering double counting the clubs.
We are actually going to get a number too big here. You're right. The reason is this. Somehow you have put the tasks in order when you didn't really mean to, right? You have earmarked one of these clubs as somehow special that you grabbed first, and then you might have other clubs that come along later. So imagine that you decided to grab the 7 of clubs, and then later on in this other choice that you're making of the rest of the hand, you happen to pick a 4 of clubs, right? So you'd have a 7 of clubs chosen here and a 4 of clubs chosen here. You're actually counting that as different than if you had chosen the 4 of clubs as the special one in the beginning, and then later on the 7 of clubs showed up in the 4 that you chose here. You've put those in order when, of course, you didn't want to, right? If the 4 of clubs and 7 of clubs are both in your hands at the end of the day, that's only one hand. We don't care whether we got the 7 of clubs here and then the 4 of clubs showed up later, or whether we started by picking the 4 of clubs and then the 7 of clubs showed up later. So this is actually a subtle mistake where we are sort of putting things in order that should not be. Okay. Yeah, so that's kind of the issue with that question.
So is the problem, so with the first one, you definitely don't have clubs in the second choice, right?
Correct, right. So you've taken out all of the hands that have no clubs. And so what are you left with? You're left with hands that have at least one club. It's exactly tightly what you wanted to count.
Okay.
Yeah, pretty cool. Yeah. question.
Could we fix the bottom one by dividing it by 2,
So,
changing the?
but what if there was a 4 of clubs, a 7 of clubs, an 8 of clubs, and a 9 of clubs that kind of came up?
Oh, I see.
So
Okay.
then the special
Not
card
really
could,
just the 2 positions.
yeah, but
Okay.
you're thinking along the right lines, like, okay, so sometimes when we overcount something, we try to fix it by either subtracting something out or dividing something out. These things sometimes can work. I'm not gonna say there'd be no way to fix this answer, but the fix that you'd have to do
Yeah.
here is so much heavier and harder than just kind of sort of taking a fresh approach at it here, in my opinion. So this is such a big deal. I actually published a paper on it in the one of the teaching journals called The Mathematics Teacher a few years ago with a student of mine who actually took combinatorics with me quite a while ago. And the journal took it and they were like, yeah, this is a subtle thing that's easy to kind of goof up. So thought I would bring it out here as well. Okay, great. One problem I always have, guys, I lose track of time because I just have so much fun with this stuff. I guess we're gonna wait and do group work next time because I don't have a lot of time. It's already 5:10. How does that happen? I tell you what I do want to do, since I have 5 minutes, I guess I could get away with this. I would like to just go through my roster really quickly. We're okay on I don't think anybody's on the waiting list. This is like. Okay, as far as that goes, but, and I know some of you, but I don't quite know all of your names. Again, I'm really gonna learn your names best. When you stop by my office, 1 or 2 or 3 at a time. But I'm gonna at least try it right now, and I just wanna see if anybody's missing as well, so. Let me go through this and then we'll call it a day. Amber is here. Where is Marion? Marion, thank you. Nikolai, where is Nikolai? I haven't seen that guy all day. He's hiding behind his water bottle. Deo Truck.
Yeah.
How do you say that?
Dow.
Dow, okay. Guys, I'm from Nebraska originally, so I'm not real good at pronouncing some of these names. You just have to correct me if I say it wrong. Where is Fernando? Fernando's here. Eduardo.
Fernando's missing.
Is Austin here? Is Austin gone? Chris Feldman. Yeah. Jose is here. Abigail.
Abby.
Abby, okay, thank you. That correct me on names of names. Khalil is here. Christian. Christian, gotcha. Mitchell. Mitchell, gotcha. Thank you, buddy. Maria.
Right here.
You're Maria.
Yes.
Okay. We've been talking like.
Yeah,
Okay.
I've been bothering you.
Is Maddie here? Oh, you're Maddie. Okay, gotcha. Now Teresa, thank you. He is here. Sean Young.
Oh, here. Oh, if you pronounce the D like a Y.
The D is a Y?
Yeah.
No, Jayan. You, oh, you. Ah, you. So you or you Yun? Just-
one.
Okay, I got it. You might have to help me with it. Kaushik? Kaushik? Thank you, sir. Arturo? All right, gotcha. Yesenia? Thank you, Yesenia. Dung Nok? Hong Nguyen? Dung Nok? Not here, okay. Luke is here somewhere. Juliet? Julie? It's my mom's name. Very nice name. Litzy? Thank you. Mario. I think I saw Mario. There he is. Diego. Gotcha, Diego. Appreciate it. TJ. Thank you. And Jasmine. Thank you, Jasmine. Alyssa. Awesome. Caden. Got it. Am I pronouncing that right? Caden? Okay. And is there anybody whose name I did not call? Are you enrolled? What is, this isn't you. is this? That's not you. So you're not on my list. Can you just double check? It starts with K. Yeah. This is you?
Yeah, that's fine.
Okay, I'm getting you two confused.
Probably, I'm not the one.
Are you, what's your last name? Oh, okay, I'm getting you two backwards. That has never happened before. I call out one name and one person says yes, and then another person says yes, and another name. Like, you guys are like trading names. Okay, I got it. I think everybody was here. And that took 5 minutes because I had a little bit of trouble with the names. Guys, thank you so much for today. We'll go ahead and call it a good day. I'm gonna be going downstairs if anybody has questions or wants to stop by. Otherwise, I'll see you on Thursday. Yeah.
Please, there's no problem.